Snowboarding, skateboarding, climbing, fun things to do. But accidents can happen. A crash, a bone fracture, and a series of surgeries. This happened to me some years ago. I broke my wrist, and thanks to a titanium implant, the bone was stabilized and healed. My wrist was blocked, and after the second surgery, I could use it again. Wouldn't it be great to avoid the second surgery? Or even better, if the implant would support the healing process itself? Here at the Helmholtz-Zentrum, we are investigating the interaction of implants with bone under different conditions. There are two main types of metallic biomaterials. There is titanium, cobalt, chrome and other implants, which are permanent, and there is degradable metallic biomaterial. And there you can find, for example, zinc or magnesium, and we are working with magnesium. The idea when we have metallic biodegradable implant is when the tissue integrity is rebuilt, you do not need anymore the stability of the implant. In other words, you have a continuous degradation of the material while the tissue is healing. When the injury has healed, the implant will have dissolved completely. When we are receiving a new material, a new alloy, the first step, of course, is to measure the degradation rate under physiological conditions in the cell culture, and to have there already the first idea if the material is degrading too fast or slow enough that we can further work in biology. When you want to test with cell culture, we have mostly two possibilities. You have the possibility to use cell line, which are immortalized, always more or less the same, and then your results are expecting to be in the same range. The second possibility is to use primary cells, and of course even better, human primary cells. There you will have also donor variation, but it's closer to the reality. Magnesium-based metallic biomaterial have some advantages and drawbacks. The greatest advantage is that you do not need a second surgery. But in the same time, its biodegradability is also a drawback, because if it's not tailored, if it's too fast, it will destroy the tissue and hinder the healing. The first test in biology will be the cytocompatibility. Here, most of the time we are working with live dead staining. It's a direct visualization of the cell's culture on the material or with extract. After microscopy, you can see directly if cells are red, they are dead, and if they are green, they are alive. And of course, we will go on only with the material with a lot of green cells. Here we'll focus our mechanistic research. In other words, which processes are influenced by magnesium and its alloys. It is very challenging because magnesium is everywhere, also in your biology, in your body, so it's also interacting everywhere in your assay, so you have to be very careful. There is a possibility of working with semi-static conditions, so normal cell culture conditions, where the cell culture media is changed every 2 to 3 days. Or you have the possibility to work with dynamic conditions with a so-called bioreactor. With this system, you can mimic the blood flow. So either fast like in the aorta or slow like in the bone. It's closer to the reality. We are unique in the world. We, together with our colleagues, are able to develop the material, test them, and understand their interaction with the biological systems. Our goal for the next years is to develop individualized implants and methods to characterize them. The possibilities are exciting. I am looking forward to what the future holds for our research, and maybe next time I break my wrist, I will receive a magnesium implant.